Now we want to move into really the last third of what we would call single variable calculus. And this is the study of what we call sequences and series, specifically infinite sequences and series. So we've been able to use the limit up to this point in order to, find the area underneath of a curve, right? Or find the slope at a specific point. Now, with sequences and series, I think that there's a very natural application of the limit. So now we want to look at, okay, what happens if we want to add something up, add up an infinite number of terms? So like, for example, what if we wanted to take the sum of 1 over n from n equals 1 to infinity? So this would look like adding 1 plus 1/2 plus 1/3. And we would keep doing that forever, right? And so what number does this equal? Does it equal anything? Is it, or does it just end up being infinity? What if we change it a little bit? What if we change it to n equals 1 to infinity of 1 over n squared? Now, so this would look like 1 plus 1/4 plus 1/9, etc., right? So the difference with these, we can see that the terms are getting smaller faster. So does that change anything, right? So typically we're just looking for, are these series, do they converge to any number? And if they do, can we find what number that is? And it's easier to just show that they do or do not converge to a number than it is to actually find that number. But for certain type of series, we will be able to actually find the number. So what we want to do first, though, is we don't want to focus on the series yet. We just want to focus on what we call the sequences. So these are simply like lists of numbers that follow a pattern. So for example, maybe we just look at the sequence 1, 1/2, 1/3, 1/4, etc. Okay. So this would be the sequence of 1 over n. And we might denote this as the sequence of 1 over n from n equals 1 to infinity. Okay. And you don't have to go to infinity. You could just go to 5 or 10 or 20 or whatever. Or maybe we do the other one, 1, 1/4, 1/9, 1/16, etc. And we would say this is the sequence of 1 over n squared from n equals 1 to infinity. Okay. So in general, we usually denote sequences by a sub n. Again, from n equals 1. Sometimes we'll do n equals 0 even. So we might have different starting points. Let's just do 1 for now. And we would say this is the sequence A1, A2, A3, etc. Right? So the indexing here, we're using the same letter but different indices, indicating that they're different numbers, but there's some kind of relationship there, right? And here, the idea is that they all follow some kind of pattern. So there's two different ways we might encounter a sequence. We might encounter like the 1 over n squared from n equals 1 to infinity, and we're told the formula for the sequence. Or maybe we would just be given a sequence of numbers, and then it would be up to us to kind of figure out what the formula is that dictates that sequence. So let's try a little bit to kind of to come up with the formula for a sequence. Okay, so this can be a little bit tricky. There's not like one way to do this, right? So we want to just kind of look at some of the common techniques here. So let's say we have the sequence -1/2, 2/3, -3/4, 4/5, -5/6, etc. So we want to try to come up with a formula for this sequence. Okay. So first of all, note the negative sign in here. Okay, so whenever there's a negative sign, so we're going to call the sequence AN. So whenever there's a negative sign, it's a good idea to have a -1 term in here raised to a certain power. And what power you want to raise it to is going to depend on where that negative is occurring. Here it's occurring on the first term, the third term, the fifth term, right? So every odd term. So if we let this be -1 to the n, okay, so n is our variable here, which dictates which term in the sequence we're at. If we let, if we looked at -1 to the n, if n is equal to 1, this is going to be -1, which is going to make the number negative, which is what we want. If n equals 2, this is going to be -1 squared, so it's going to be positive. So that term is going to be positive. So that's what we want here because our second term is positive. N equals 3, it's going to be negative again, and that's what we want because our third term is negative. So this is a good trick here for when we have negative terms in the sequence. Now we want to look for some kind of relation between the numbers here. So we can see that the numbers on top are always going up by 1. The numbers on bottom are always going up by 1. Also, the numbers on the bottom are 1 more than the numbers on the top. So for this one, we could simply do n, because it does start at 1, over n plus 1. Okay, so then when n equals 1, we'll have -1/2. When n equals 2, we'll have 2 over 3. Okay, etc. So yeah, so that's all we would do for this one. We'd come up with this formula. So why would we want to even bother coming up with these formulas? Well, now this is going to allow us to find what this sequence converges to, if anything. So we can just do this simply by taking a limit, and we'll look at that in a separate video, but just think about if we took the limit as n goes to infinity here, we might be able to see whether this is converging to a number or not. If we ignore the -1 part, we could see that it is converging to 1. But the -1 part is going to make it tricky because it's going to constantly flip-flop between negative to positive. So it's going around like -1 to +1. So that's going to keep it from converging. Okay, but we need this formula before we can even think about these things. So let's look at another example. Let's say we have 3/4, 9/7, 27/10, 81/13, 243/16. Okay. So we want to look for some pattern here. So you might notice that the top numbers are powers of 3. And then you might notice that the bottom number, the numbers are increasing by 3 in every term. Okay. So the first thing we can note is that the top numbers could just be 3 to the n, right? So 3 to the first, 3 to the second, 3 to the third, etc. The bottom's numbers then, if we want this to start at n equals 1, then we should make this 3n plus 1, right? Because then when we put in 1, we'll have 4. When we put in 2, this will be 6, and then we'll add 1 and we'll get 7. Okay. So this will make it start at 4 essentially, and then because the 3 is being multiplied by n, it's going to increase by 3 every single time. Okay. Now if we think about this limit, it doesn't seem like it's going to converge to anything at all. 3 to the n is increasing way faster than 3n plus 1. So this one's probably not converging to anything. Okay. All right, let's look at another one here. So I have 1/5, -1/7, 1/9, -1/11. Okay, and that's it. So again, the top number we want to have some kind of -1. Now, it's not starting at the first term, or rather, the first term is not negative, is what I mean to say, right? So maybe we make this n plus 1 as the power. Because now when we plug in 1, we'll get -1 squared, which is positive, and then it'll alternate from there. And then we don't need anything else on the top because the top is always just 1. The bottom is always increasing by 2, right? And it's starting at 5. So maybe we can make it 2n plus 1. Or sorry, this should be 4n plus 1. No. Sorry, it can be a little bit tricky to come up with this. It should be 2n plus 3, right? So it needs to be 2n because this will let it increase by 2 every time, which is what it's doing. The plus 3 lets us adjust for where the sequence is starting. Okay. So we need this to be 2n because it's going up by 2. And then we look at, okay, if we put in n equals 1, it's going to be just the 2n part, it's going to be 2. So we add 3 to it to bring it to 5. Okay, so that makes our starting point 5, and then it'll increase by 2 from there. Okay, I just want to look at one more here. So let's look at sequence right here, which is 2 -2/3, 2 9ths, -2 27ths, 2 81st. Okay. And then it's going to go on forever. So by the way, that dot 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 means it goes on forever. I don't think I ever explicitly said that, but that's what it represents, right? So this means that it's an infinite sequence. So this one is a little bit, not strange, but it's a little bit different from what we've seen because now the number on top is 2 every time, but that's not going to change too much. So again, let's think about what's happening here. First of all, we have that -1 and it starts on the second term. So we should make this a -1 to the n plus 1. Or we might want to do n minus 1, depending on where you're going to start your sequence, if you're going to start it at 0. Then we see that on the bottom, so if we put a 1 on the bottom of this one, just for consistency's sake, we see that the bottom consists of powers of 3. Now, 1 still fits into that pattern because that could be 3 to the 0, right? So the first term is 3 to the 0th. The second term is 3 to the first, right? So let me write these out. Right, so we have 3 to the 0th, 3 to the first, 3 squared, 3 to the third, 3 to the fourth, right? So that's fine, but we need to take into account that the power is 1 less than the current term, right? So if we're going to start our sequence at 1, then the bottom here, is going to be 3 to the n minus 1. Okay. And then the top, of course, should have a 2 in there. Okay. Now, this is fine how it's written, but it might be in our interest to kind of combine this a little bit because n plus 1 and n minus 1 don't really have any difference in terms of how the -1 is concerned, right? Because -1 to the 0th is still 1. So we could change that to an n minus 1. And then this allows us to rewrite this as 2 to the negative times -1/3 to the n minus 1 power. So it just lets us write it a little bit cleaner. It also puts it in the form of what's called a geometric series. or sequence rather, not series. Okay, so a geometric sequence is one where the ratio of every pair of terms is the same. So if you take the ratio of 2 and negative 2/3, it'll be the same as the ratio of negative 2/3 and 2/9, for example. So this is one that comes up a lot because it has a really nice formula for the infinite series version of these, and it allows us to calculate what number it converges to pretty easily. Okay. So in particular, this term in the middle here, the R, we call R. I'm trying to point, but my cursor's not coming up and I keep forgetting. But it's going to have something like A, we usually say, like A sub 0 or A sub 1 or whatever the first term is, times some absolute value of, or no, we don't call it the absolute value, but we say R to the n, where R, the absolute value of R, is between 0 and 1. Okay. So something like this of this form is what we call a geometric sequence. So we'll talk about it a little bit more when we talk about the series version, because like I said, they come up often and they have a nice formula. But yeah, so next we'll look at the limits of sequences.